In this lesson, we're going to continue our look at descriptive statistics. Lastly, we looked at central tendency, how things cluster. Today, we want to look at how they spread out. We call that dispersion, and how spread out the data is. One of the best ways of measuring dispersion is something called the standard deviation. What it does is it measures the average deviation or difference between each individual piece of data and the mean. The bigger your standard deviation, the more spread out things are. However, it's really used as a comparative purpose. And by itself, it's not that meaningful. We like to use it to compare two sets of data. So if I have a standard deviation in one class of 10 and another standard deviation in a second class of 6, the fact that 6 is smaller than 10 tells me in that class, my data is closer together. The smaller is better, closer, consistent. Okay, to measure standard deviation, we have these lovely formulas. Again, populations and samples. We're generally going to do samples. That's kind of how we do data because we don't know how many pieces of data are all together. We assume everything is samples, but just so you know, there are two of them. They're basically done the same way. Our standard deviation, we call this sigma, is found by the square root of the sum of each data value minus the mean, and we're going to square it. And we're going to add up each one of those things, divide by the number of pieces of data, and then square root it. Now, it seems really complicated. We're going to do one. We'll see how it works. It's actually not that bad. It's just kind of time consuming. So, standard deviation of these numbers. The first thing we have to do, and we're going to assume this is a sample, is figure out our mean. So old-fashioned, add them all up, and divide by how many there are. And there's 1, 2, 3, 4, 5, 6, 7 of them. So plug them into your calculator, add them up. We should get a mean of 12 if you do it properly. Okay, we need that to know where average is so we can calculate our standard deviation. So we're going to use SX. We're going to use the sample version. Unless I say otherwise, always use the sample one, okay? So the sample is found by the big giant square root of each value. Well, my first value is 7 minus the mean squared plus the next value minus the mean squared plus the next value minus the mean squared, and so on and so on and so on, all the way to the end. That's why I said it's not hard, it's just time consuming. I'm going to run a room here. Hang on one second. I'll move this all over. Got 15, I need 14 and 19. And then we're going to divide that all by the number of pieces of data, which we've already figured out is 7, and subtract 1. The reason we subtract 1 is that makes something a sample. If we had all 7 things and there was only 7 things, it'd be a population. So to do a sample calculation, we always subtract 1. Okay, next step. We are going to subtract and square root. So I get negative 5 squared is 25. 3 squared is 9. 0 squared is 0. 4 squared is 16. 3 squared is 9. 2 squared is 4. And 7 squared is 49. And on the bottom we get 6. Okay. If you use your calculator, use your calculator. We're going to add them all up. So 25 plus 9 plus 0, 16, 9, 4, and 49 comes out to 112. Okay, we're going to do our division first. So divide 112 by 6, get your answer, and then square root it. And if you did it right, you should get 4.32. That's the standard deviation of this data. By itself, it doesn't have much meaning. Let's pretend that was a quiz, and those are our marks on the quiz. Well, based on that quiz, standard deviation is 4.32. However, if I did another quiz, and the standard deviation of that quiz was 2.1, well, that just tells me that this data over here is more consistent. It's got a smaller deviation, smaller changes between each piece of data and the average. Another commonly used measure is something called the variance. All it is the standard deviation squared. Okay, so literally take your number and square it. You don't have to do any new calculations other than that. Okay, we don't usually use it in addition to standard deviation. We use it instead of. So it's one or the other, the variance or the standard deviation. They're just two different measures that do sort of the same thing. Okay, of course, we can always use range, quartiles, interquartile range to also describe the spread. But we usually use that as like a box and whisker plot to show that spread. take a look at another example. The number of eggs laid by a group of chickens in 1 month are as follows. I want to find a whole bunch of things about that. All my measures of central tendency and our new ones are measures of spread. But I don't want to do this by hand. I want to use my technology. So with our graphing calculators, we know we have to enter our data. That's always our first stage. So let's turn it on. Go that way. Put in our data. Then we can do our calculations. So stat. I want to go over to calc like we did yesterday. One of our stats like we did yesterday. And still our data is in L1, nothing in frequency list. You go down to calculate. If you do that, you can get a big giant set of things, of which we now know what most of them are. So what do we need first? We need our mean. And it's a sample, right? The number of eggs in 1 month, just 1 month is a sample. So 27.84. We want our median. We know we can find that further down the list. So go down your list. We want a median of 27. Our mode. I can look at my list I was given in the question. Most common number. I see 3 27s. I don't see anything else that repeats 3 times, so our mode is 27. Okay, our range. Part B. Our range is our highest and our lowest. Now the nice thing is our graphing calculator has those too. Okay, that's got a max, that's the very bottom one, of 35, minus a min of 20, gives me a range of 15. Okay, I have an IQR, I can find that also from this list. Q3 is 31, Q1 is 25, so my IQR is 6. Okay, the new ones for today, let's move this over here. I want standard deviation. So standard deviation is also on our list. If you go back up, we're looking for the one that has the SX. Now notice it has both standard deviations, S and the fancy O, the sigma. Make sure you're using S. So 4.44. And our standard deviation squared, our variance, we literally square it. We're going to take this number and square it, and you should get 19.71. There's our calculations. Okay, part D. On another farm, the mean is 27.1 eggs, the standard deviation of 1.21. So we're comparing. If we're purchasing eggs for a grocery store, which farm would you want as your supplier? So we need to compare our numbers, so standard deviation and mean, to the other farm, standard deviation and mean. Which farm is better? Well, look at the average. This farm, farm number 1, looks better. But looking at my standard deviation, my consistency value, and remember low is good, farm number 2 is better. So how do I answer this question? And really there actually isn't a wrong answer to this question. There's better answers and worse answers, but no wrong answer. I would suggest that farm number 2 is better. Right? And the reason I would say that is because on average, it is roughly the same. But more importantly for us, if we're purchasing eggs, it is way more consistent. I know what to expect from this farm. I'm going to get most days 27 and not have a whole lot of difference from that. My standard deviation is 1.21, so usually what we talk about this number is most of the time you'll be within 1 standard deviation of the mean. So most days I'd be, I don't know, 26 to 28. Okay? Whereas the second farm, a standard deviation of 4, means some days I may only get 23 eggs, other days I may get 31. So I might luck out and get some really good days, but equally likely to get some pretty bad days. And in a grocery store, you want to sell the eggs, you kind of need to know what you're getting. Okay, so that's how we can use standard deviation. Our second idea from today, also about spread, is something called a z-score. Okay, and again, it uses standard deviations, but here, what a z-score does is it measures how many standard deviations a single value is from the mean. Again, it's a comparative tool. Okay? The bigger your z-score, the further you are from mean. Maybe above it, maybe below it, but you're a long ways from the mean. A small z-score, you're pretty close to the mean. A z-score of 0, you are on the mean. Okay? Again, we have populations and samples, so the calculation is the same, just the symbols are different. A z-score is found by your value minus the mean divided by the standard deviation. And that's true for over here, sorry, this one, the mean and the standard deviation. Okay? If a z-score is negative, it just tells you you're below average. Positive, you're above average. Remember, average is the mean. Okay? And some general rules, if you're less than 1 standard deviation of the mean, you're real close to average, hardly any different from average. Okay? If you are between 1 and 2, you're moderately far from average. You're a little bit better, a little bit worse. 2 and 3 is pretty far above average. Like it's unusual to get 2 above 3. And if you're more than 3 standard deviations, that's extremely far from average. You'll rarely see more than 3 standard deviations. It's very, very unlikely. All right, so how do I work this? I got a randomly selected chicken. It was found to produce 32 eggs. How productive was this chicken compared to the rest? And let's do it in terms of farm number 1. Okay, so my farm number 1 average, we'll go back for a second here to our average, was 27.84 and a standard deviation of 4.44. 27.84 and our standard deviation was 4.44. So I'm comparing this one chicken to everybody else. Its z-score, 32 is its value. The mean is 27.84, standard deviation of 4.44. So we end up with on top, what's that, 4.16 over 4.44. It's a positive number of 0.94. So that's above average. It's bigger, it's a positive number, but not by much. It's within 1 standard deviation. It's kind of normal. Slightly above, but kind of normal. Okay, let's take a look at the next example. We got Emma. This table shows Emma's exam results from last year. In comparison to her classmates, in which course did Emma do the best in? Now, notice it was said in comparison to her classmates, because by herself, if I look at Emma's scores, obviously the best mark is math, right? She got 84. That's awesome. She did not just as good in English, but it's relative to her classmates. So let's take a look at her z-scores, because z-scores compare one person, in this case Emma, to everybody else, her class. So if we look at English, in English she scored 48. Class average was 40. Standard deviation was 4.4. So her z-score in English was 1.82. So she's good. She's above average, fairly decently above average. If we try French, same idea. She scored 81. Average was 60. Ooh, class did not do good, but standard deviation was 9. Lots of inconsistency there. She scored 2.33. So she was really high compared to average. And let's try math, which she did really well on, right? Well, math, the class didn't do so good. The average was 55, but standard deviation was huge. It was 18. Really inconsistent. 1.61. So just on these 3 classes alone, even though she had the highest mark in math, it actually was her worst class relative to her classmates because it had the lowest z-score. And we'll try bio. Bio is a tricky class. She got 68, didn't do so well in it. But the class only got 50, and there's a huge amount of inconsistency. Z-score there, 0.9. And then geography, she had 84. Some inconsistencies again. And her z-score was 2.27. So relative to her classmates, her best class was actually French. Even though it wasn't her highest mark, it's because of the variables of inconsistency and average. Homework for today, you can try. Give them a try. If you're stuck, come see me.